Questions 21 through 25 on the 2004 Grade 10 AMC 10B. Let 14 ... and 916 ... be two arithmetic progressions. The set S is the union of the first 2004 terms of each sequence. How many distinct numbers are there in S? So the first arithmetic progression will basically be of the form 1, 4, ... correct? But in this case, A is equal to 1 and D is equal to 3. That's the difference. So therefore, this one will basically look like 1, 4, 7, 10, 13, and so on. So I'll write out a few of them. And the next one is 9, 16, ... And in that case, A is 9, and the difference in this one is 7. So I'll write out a few of those. And the first sequence, every term, A to the n, is basically of the form 1 plus 3 times n minus 1. And if you simplify that, it basically becomes 3n minus 2, like that. In the second arithmetic progression, each term, A to the k, is of the form 9 plus 7 times k minus 1. And this simplifies to 7k plus 2. Okay? Now let's concentrate on what is it that they're asking us. They're basically saying they want you to write out the first 2004 terms. So in here and here. Well, I don't think they really want you to write them out. They want you to analyze what they are. And then if you look at those 2004 terms from each sequence, there will be a total of 4,008 of them, correct? Now they want you to find the number of distinct terms. Now, what do they mean by that? Basically, in each sequence, I hope you can see that there's going to be some numbers that appear in both. So, for example, the 16 appears in this one, it appears in that one. And there's others too. 37 appears in that sequence, also appears in this one. 58 appears in this one, also appears in that one. So these numbers that I just circled appear in both sequences. So when you add up all the 2004 here and the 2004 here and add them, you will get 4,008 numbers, but some of them you have double counted. They want you to subtract those double counted numbers and come up with a list of distinct numbers. All right? So that's what we have to do in this question, is find out how many numbers like this exist. How many numbers are in both sequences? So the first step is to understand that each term in the first sequence is of the form 3n minus 2, and each term in the second sequence is of the form 7k plus 2. So we let those equal to each other. 3n minus 2 is equal to 7k plus 2. And this will give you a way to solve for n and k. So we got 3n minus 7k is equal to 4. And therefore 3n is equal to 4 plus 7k. N is therefore equal to 4 plus 7k over 3. All right? And our boundaries basically are for n is between 2004 and 1, and k is also between 2004 and 1. So let's make a list, not too long, but hopefully just enough that we can kind of get an understanding of any sort of pattern. So an, the nth term in the first one, k is going to be the kth term in the second arithmetic progression, and the value for n and the value for k. Okay, let's proceed and see what we get. So, for the first one, I actually circled them in the diagram above. 16, 37, and 58. Those are the ones that are common, because that's what we are most interested in. So 16 37, and 58. Those are the ones we got very quickly just by inspection. Now, what is n and k? That's what we are interested in. Well, when the term is 16, n was equal to 6. And the k, therefore, is 2. How do I know that? Well, I just counted, basically. 1, 2, 3, 4, 5, 6. It was the 6th term in the first one, and it was the 2nd term in the second one. And then in a very similar way, it was 13 for n and 5 for k. And for 58, it was the 20th term for n, and it was the 8th term. Now we need to find more values for n and k to see if we can get some sort of a pattern. And if I keep going like this, using this formula, I'll get 27n and 11 for k. And when I do that, my term will be 79. And so on. You keep going like this. And these are the numbers that appear in both lists. And therefore, those are the ones that we will have to subtract. All right, we have to find how many of these are there. So far, we found 4, right? We have to find how many of them are there, and we subtract that number from 4008. Well, one thing you have to remember is that we got to keep in mind these boundaries here, right? That will help us understand how far we can go for k and n. Now, one thing I noticed is that k is smaller than n. So therefore, I can go up to about 2004 for both of these. That's the maximum. So let's see what I can get. For 2004, if n is 2004, if I plug it into here, I don't get an integer value for k. I have to have integer values, right? Because k represents a certain number term. It's the 7th term or the 100th term, like that. K can't be, 52.6. So 2004 for n doesn't work, but 2001 does. When n is 2001, k is 857. So this is the limit. We can't go anything farther than that because there's only 2004 terms. All right? Now, when you get up to here, that's it. N is 6, 13, 20, 27, ... all the way up till 2001. And for each of these n's, you'll get a certain number. All right? So now we have to figure out how many n's did I get in that list. With a little bit of number manipulation, you can figure out that all you have to do is take 2001, subtract from it this original 6, and then divide that by 7. And you'll get 285. That's how many n's you'll get in this list. 6, 3, 20, 27, so on, all the way up to 2001. But you have to add one more, because this mathematical equation doesn't account for the very first one. So I've got a total of 286 n's. There will be a corresponding 286 k's, and each of those will produce a number that appears in both arithmetic progressions. So this is the number that you have to subtract from 4008. So let's do that. 4008 minus 286, and that is equal to 3722. These 3,722 numbers will be unique. There will be no numbers double counted. So the answer, 3722 for 21, is A. A triangle with sides 5, 12, and 13 has both an inscribed and a circumscribed circle. What is the distance between the centers of those circles? So let's first draw a diagram. So this is basically our diagram. We've got a triangle, got two circles, one inside, one outside. And let's label this. This is 5, this distance. That's 12, and that's 13 over there. Now, one thing I immediately noticed, 5, 12, 13 is a Pythagorean relationship, correct? And therefore, this is a right angle. Now, if that is the case, then that means that this is the diameter of the circle. Why? Because if you have the diameter and then you draw any angle that starts from the edges of that diameter, that will be a right angle. So they both go hand in hand. If this is a right angle, then this is a diameter. If that was the diameter, if they told you that in the question, then that would mean that that is a right angle. Both go hand in hand. One means the other one is true. So therefore, I can label this if you really want to. I don't really need to, but just remember this is the diameter right there. Okay? So if that's the diameter, immediately we know that diameter is equal to 13, and therefore the radius of that big circle is 6.5, half of the diameter. Okay? So that's a very important piece of information right there. Now what I'm going to do is I'm going to go back to the diagram, revisit that diagram, and start drawing in some what I hope is helpful information. So first is a line from the center to the tangent point like that. Another is from the center down to the tangent point like that. And another one from the center to the tangent point on the diameter of the big circle. Okay? And then I'm going to draw the center of the big circle, so approximately here, I believe. That should be that red dot. And let's draw now what they want you to figure out in the question, which is the distance between the centers of these two circles. So approximately like that. That red line represents the distance from the big circle center to the small centers, to the small circle's center. And there's some right angles in here. This is a right angle right there. This is a right angle because those are tangents, right? And this is a right angle also. Okay, so far, no confusion, I hope, with the labeling. A little bit more labeling, I promise, and then we can proceed with the question. Now I'm going to draw a line from the center of the small circle to the vertice of that triangle, and then a very similar way, I'm going to draw one on the other side. So this should be enough for us to solve this question. All right, now here we go. These lines right here, this one right here, this one right here, and this one, they all represent the radius of that small circle. All right, so I'll write that in R, small r. And then the line from the center of the small circle to the center of the big circle, I'll call that D. That is what we were trying to figure out, basically. Now, if from here to here is R, and this whole distance is 12, that means this distance from here to here is 12 minus R. Like that. And this distance from here to here is also going to be 12 minus R because those two triangles are congruent. So 12 minus R. The distance from here till there. Okay? They have the same angles, those triangles, and the same sides. Exact same. In a very similar way, if this is R and this whole region is 5, then that means from here to here is 5 minus R. Like that. And exactly the same way, these two triangles, that one and this one right here, are congruent. They're pretty much the same. They have the same angles, the same sides. So therefore this section of the diagram is also 5 minus r. So that means that from here to here is 12 minus r, from here to here is 5 minus r, and if you add those two, they must equal 13. So 12 minus r plus 5 minus r is equal to 13. And therefore we've got 17 minus 2r is 13. That means 4 is equal to 2r, and therefore r is equal to 2. The radius of the small circle is 2. And now we can turn our attention to this little triangle in the middle here, that one right there, and we can solve for d. We've got r is equal to 2, but what about this distance here? That little distance there, that side of the triangle. That shouldn't be a problem because this is, of course, the center of the large circle, correct? So if I draw a line from that center to the edge, it represents the radius of the large circle. And that we've already figured out was 6.5. And then this from here to here is 5 minus r, but r is 2. So that is actually equal to 3. I could just put that in there. So therefore, since this is 6.5 and that is 3, this distance in here, right there, will be 6.5 minus 3, which is 3.5. And I know it doesn't look like it, but it's not drawn to scale, but it's okay. You understand the question so far. All right, I think that's it. I think I can solve this without too much space. I can just use Pythagoras on that little triangle right there. So what do I have? I've got r squared plus 3.5, which is 7 over 2 squared, is equal to d squared. R is 2, so I've got 2 squared, which is 4, plus 49 over 4 is equal to d squared. Correct? And then let's see here, this gives me 16 over 4 plus 49 over 4 is equal to d squared, and that's basically 65 over 4, and therefore if you take the square root of both sides, you'll get 65 over 2 is equal to d. And therefore 22, the answer is D. Each face of a cube is painted either red or blue, each with a probability of 1/2. The color of each face is determined independently. What is the probability that the painted cube can be placed on a horizontal surface so that the 4 vertical faces are all the same color? So you've got a cube, and what they're basically saying is that you're going to paint all the sides either red or blue, right? And then you're going to put it on a table or horizontal surface. And they want these faces, I'll put a check mark, this one, the one behind, and the one on the side. Those are the vertical faces. They want those vertical faces to be all the same color. They don't care about what's on here, the top, and they don't care what's on the bottom. They just want those 4 vertical faces to be the same color. So let's figure this out. What can we do here? Well, first and foremost, the very first thing in any probability question is to figure out what is the total number of possibilities. Well, we've got 6 faces, right? 1, 2, 3, 4, 5, 6, and each face, there's 2 possible choices, red or blue. 2, 2, 2, 2, 2. And then you multiply them all. And therefore 2 times 2, 6 times 2 to the power of 6, which is 64. That is the number of different ways that this cube can be painted in terms of the sides. Okay, so that's our total. Now we have to figure out how many fulfill that condition. And to do that, we have to look at 3 scenarios. The first scenario is probably the easiest one to explain, which is all the sides are the same. That means they're all red or they're all blue. If that happens, our condition is met, right? Now you say, well, that's not what they're saying. They're saying they just want the four vertical faces to be the same. Yes, but they don't care about what's on the top, what's on the bottom. If you have all red, the condition is met. And if you have all blue, the condition is met. The four vertical faces will all be the same color. So how many ways can you get this guy here, the first one? Well, there's only one way, which is basically have all six sides red. And how about the next one? And in a very similar way, you can conclude there's only one way. So that is probably the simpler one to explain. The next scenario that meets the condition in the question is if one side is a different color. So what does that mean? It means that you've got, let's say, all red, but then one side is blue, like that. If that's the case, you can just put the blue on the top, or you can put the blue on the bottom when you place this cube on the horizontal surface, and therefore the remaining 5 sides will fulfill the condition that all 4 vertical faces are the same color. Now, how many ways are there to do this? Well, the blue side can be any of those sides. So you just have to keep moving the blue around. And if you do that, you'll see that this is 6 ways of doing that. But what about for blue? Right? We did this for R being the dominant color. We can do the exact same thing for blue in the following way. You got blue, 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 and then one side is different, so I make that one side R. Okay? So basically that type of a scenario, and there's 6 ways of doing that. So I hope you're convinced that these satisfy the condition that if you take any of these scenarios and you put the odd guy out on the top or on the bottom, the remaining will be able to satisfy the condition of showing 4 vertical faces as the same color. But we're not done. We've got a few more. We've got another scenario, and that final third scenario is when you have 2 sides that are different color. So something like this. You've got red, you got 4 blues, and then you've got a red like that. Okay? And you might say, okay, well, that seems like the only way of doing it, but there's actually 3 ways of doing this. And that's the part of the question I think that is challenging. But I'll try to show it to you in a 3D way. So the first one, right, is basically this is going to be blue here, blue there, and blue on the side, and the reds will be on the top. Okay? Satisfies our condition, no problem. But then you say, well, the next guy that you wrote is exactly the same. How is that a different way? Well, it is because the blues are going to be now top, bottom, front, back, and the reds are on the side. You say, well, that doesn't satisfy my condition. My condition says that the 4 vertical faces have to be the same. Yes, but you can take this cube and put it on that side as the bottom. You can just flip the cube, make this the bottom. You see what I mean? And then this becomes a top. So that's why that condition satisfies the question stem. And in the exact same way, the third one here, we took care of that one. The third one here also satisfies it. How? Put the reds as this one and the one behind, and the blues will be top, bottom, on the side here, and on the side here. And in a very similar way, if you take this guy and make that the bottom, you just flip the cube over, it will basically satisfy the condition. So I think that's the most challenging part of this question, is visualizing the fact that when you have this scenario, two sides different, there's actually three ways of doing it. And in a very similar way, there's another three ways of doing it with four reds, where this is blue and this is blue. So if you can visualize that, then you'll be able to get this question. And this gives you another three ways. So in total, how many do we have? We had 1, 2, 6, 6, 3, and 3. That total is 12 plus 2 is 14. 14 plus 6 is 20. So remember, our total was 64. So our probability, I can put it in here somewhere, 20 over 64. That's my probability. In lowest terms, that would be, what, 10 over 32, 5 over 16. And therefore, number 23 is B. In triangle ABC, we have AB is equal to 7, AC is equal to 8, and BC equals 9. Point D is on the circumscribed circle of the triangle, and AD bisects angle BAC. What is the value of AC over DC? So, I first want to teach you a couple things. The first thing is called the angle bisector theorem. If you remember, the question stem talks about an angle being cut in half. And angle bisector theorem basically means that if you've got a triangle like this one right here, and you basically draw a line like that cuts an angle in half, and that's what they've done there. They've drawn these tiny little lines to indicate that those two angles are the same. If you do that and you label the other sides as they have, A, B, C, and D, then this relationship is true. A over C is equal to B over D. So that's the first part of the primer that I wanted to teach you. The next one I can just draw for you. It's known as the Inscribed angle theorem. And this theorem basically states that, let's say you got 2 points on your circle, right? Any 2 points, doesn't really matter. A and B. And then from those 2 points, let's say I draw lines to the opposing point like this. Okay? And then I do that again, but this time I draw it to a different point on the circle using the same 2 points, A and B, but I draw 2 lines meeting at a different point on the circle. The inscribed angle theorem states that these 2 angles will be the same. Okay? As long as those 2 lines originate from the same points, and in our diagram those points are A and B. Alright, so these 2 theorems we're going to use in our question. So here's our question again. Now let's draw a diagram to illustrate what they're talking about. So here's our circle, and I'll label this A, and this point B, and this point C. And they tell us that AC is 7, AB is 7 rather, AC is 8, and BC over here is 9, like that. I'll just write 9 over here. And then they give us a very important clue, which is that you are going to draw a line that bisects angle BAC. So this angle right here is being bisected by a line. So I'm drawing that line in a way so that that angle is cut in half. And I'll draw it all the way to the edge of the circle, like that. And they tell you that when you do that, the point where it touches the circle is D, right here. Okay? And then this point right here where the green line cuts the triangle, I'll call that point E. Okay. And I think that's about it so far. So now we are going to use the first of our theorems, and that was this guy right here, the angle bisector theorem. A over C is equal to B over D. So let's see if you can use that in our diagram. In this diagram, that would basically mean that 7 over right here, BE, is equal to 8 over this side, EC, like that. That's using that theorem. Okay? Now, 7 over BE is equal to 8 over EC, but EC basically you can write in terms of BE. How? This whole side BC is given to us as 9, correct? Well, then EC is going to be just 9 minus BE, like that. All right, and we can now solve for BE. So we got cross multiply, you get 63 minus 7 BE is equal to 8 BE. And this looks like 63 is equal to 15 BE. And therefore the length of BE is 63 divided by 15. Which is that in those terms it can be 21 over, you're dividing by 3, right? So 5. 21 over 5. Okay. Now we get to the next part, which is this theorem, the inscribed angle theorem. If you got 2 points and you draw lines from those 2 points that reach the other end of the circle and they make angles, those 2 angles will be the same. So can you see that in here? I'll give you a hint. Use these 2 points, A and C. Well, the first one is this angle right here. I'll call that Y. And the other one, I didn't draw it in for you, so sorry about that. But it would basically be from C to D. That one right there. Okay? So, the first one was from A and C, that angle, and use the exact same 2 points A and C and draw another angle, and there you go. This one will be the same. That's that second theorem known as the inscribed angle theorem, and therefore this is also equal to Y. All right? Now, do we know any other clues? Well, there's that big one that they gave us in the question, which is that the point D is on the circumscribed circle of the triangle, so that AD bisects BAC. AD, this line, bisects BAC. So that means this is X and this is X. All right. Now we've got 2 similar triangles. 2 triangles that have all the same angles. And those triangles are triangle ABE and triangle ADC. So you've got 2 triangles that are similar. Which one's ABE? Right here, which has the angles X, Y, and the third angle will basically be 180 minus X minus Y. And then you've got ADC, which is this triangle right here, which has X and Y, and the third angle will be 180 minus X minus Y. So those 2 triangles are similar, and therefore that means that the ratio of their sides is the same. So we have AB over BE, AB right here, and BE right here, is equal to AD over CD. AD right here, and CD right here. And let's see how much of this information we already have. AB we know is 7. And BE we figure out here as 21 over 5. And AD over CD, the good news is that is exactly what they want us to figure out in the question, AD over CD. And we can do that. 7 over 1, invert and multiply, you get 5 over 21. And this looks like 5, divide top and bottom by 7 there, you get 5 over 3. AD over CD. There you go, that's the answer. So number 24, the answer is B. A circle of radius 1 is internally tangent to two circles of radius 2 at points A and B, where AB is a diameter of the smaller circle. What is the area of the region shaded in the figure that is outside the smaller circle and inside each of the two larger circles? So this is our diagram, and we basically have to figure out the area of the shaded region. So first I'll give you the strategy, and then once I give you the strategy, I'll proceed. Area of the shaded region will basically be the area that is common to the two circles, subtract the small circle, which is going to be pi small r squared. Now, what area is common to the two circles? It's this one right here. That is common to both circles, and if we find that and we subtract from that the small circle, we will get the shaded region. Now, the good news is that the small circle has a radius of 1, so this part just becomes pi 1 squared, and this is just the area of the common region minus pi. So in the next part of the question, I will concentrate on finding the common area. So here's the diagram again, and I'm interested in finding the common region to these two circles that are identical. Now, these circles have certain properties, right? We know that they have both a radius of 2, and they basically have center points right here and right here. And if you were to draw a line from those two center points, they basically would join like that, and that line would have a length of 2. Why? Because it essentially represents the radius. Okay, so that's the first part of this diagram. The next part is I'm going to draw lines to make triangles. So I've got a line from there to there, a line from there to there, and very similarly lines on the other side like that. Now let's talk about these lines. What do they represent? This first line we already discussed was the radius of either circle. What about this line here? That's also the radius of this circle on the bottom, so that is 2. And then this line represents the radius of the top circle, so that's also 2. So therefore this is an equilateral triangle, and in a very similar way, that's 2 and that's 2. So there you go. Now to find the common region to these two circles, which I previously highlighted, it's basically this one right here, that region right there, we have a certain strategy. We have to find the area of the two equilateral triangles, and then we have to find the area of this region that I'm labeling as A. And there are 4 identical regions of that kind. So the area that is common to those two circles will be the 2 equilateral triangles plus 4 of those A's. So let's first proceed with the equilateral triangle. So each of those equilateral triangles basically looks like this that I just drew on the side. We've got side lengths of 2, and we therefore need to find the area. So to find the area, I'm just going to draw a perpendicular from one side to the other, like that. And that will therefore cut this in half. This will be 1 and this will be 1. And we can easily figure out this length by Pythagoras. Basically, if we call that height, it'll be h squared plus 1 squared is equal to 2 squared. And therefore, h squared is equal to 4 minus 1, which is 3, and h is root 3. Okay, so therefore, each of these equilateral triangles has an area as follows: 1/2 base, which is 2, times height, which we just figured out was root 3. And keep in mind that there's 2 of them, so I'll just multiply by 2, like that. Now I have to figure out my area for A. Now how do I do that? Concentrate on this region right here, from there to there, and then across the circle. That is a pi, correct? And that pi will allow me to figure out region A. If I can figure out the area of pi and then subtract from it the area of the equilateral triangle, I will get A. So how do I figure out the area of that pi? That pi is essentially just a segment of the area of the circle. A circle of radius 2, pi r squared. But how much of the circle? Well, remember this was an equilateral triangle, so this is 60 degrees. So 60 is what you would place here. And then, once you have that, you would subtract from it the area of the equilateral triangle. And that would give you A. So first, let's just figure out the area of the pi. So this will be 1 over 6 pi times 4. So this becomes 4 pi over 6. And then to get A, I would take my pi, which is this whole region, and I would subtract from it this equilateral triangle. And if I do that, I will get the area for A. So A is basically the pi, which is 4 pi over 6. Subtract from it the area of the equilateral triangle, which is 1/2 base, right here, 2, times height, which is root 3. And therefore, we've got 2 pi over 3 in lowest terms minus root 3. There you have it. And now we can substitute that into here. So AC will then become 2 root 3 plus 4 times 2 pi over 3 minus root 3, like this. And this becomes 2 root 3 plus 8 pi over 3 minus 4 root 3. And this becomes 8 pi over 3 minus 2 root 3. This is the area of the common region. So we'll take that and place that into the first part of the equation, which is right here. Area of the shaded region is the area of the common region minus pi r squared. And since the small r was 1, we got AC minus pi. What did we get for our AC? Our common region, we got right here, 8 pi over 3 minus 2 root 3. 8 pi over 3 minus 2 root 3. And then don't forget this minus pi. So we get a common denominator. And that will be 8 pi minus 3 pi, which is 5 pi over 3 minus 2 root 3. That is the area of the shaded region. And let's see the answer choices. 5 pi divided by 3 minus 2 root 3 for number 25 is answer choice B.